Okay, so I wanted to talk about electric flux and Gauss's law. This is the section in that chapter on continuous charge distributions and Gauss's law. So Gauss's law is one of these things that's a fundamental idea in electrostatics, and what we're going to do is see how to use it to solve some problems that are maybe a little bit more difficult to solve, sort of the brute force way that we tried in the beginning, where we divided up the charge and calculated the electric field due to that charge distribution. Gauss's law can help us do some of these problems in a simpler way if we have a nice geometry. So if we have spherical symmetry, or we have cylindrical symmetry like a line of charge, or planar symmetry, then Gauss's law gives us a way to solve these problems a little bit simpler. But Gauss's law is an important fundamental result in electrostatics. So it starts with this idea of electric flux. Electric flux. So flux is how much electric field do you have in a given region? It's a field times an area, basically, okay? So let's say that you have a plane, just some planar area, and there's an electric field in the region. So here's an electric field. Okay, and I think of this electric field as permeating this entire region. I'm drawing it as one vector, but I think of the electric field as being uniform throughout this region. What we do is we represent the area that you have, this little plane that I've drawn, represent this area with the so-called area vector. The area vector is a simple idea. That area vector is a vector that is perpendicular to the area, okay? And the magnitude of the vector represents the area. So it's perpendicular to, if it's a nice smooth plane, it's perpendicular to that plane, or so-called normal to the plane, and the magnitude of the vector represents the area. So an area vector for this plane that I've drawn, let's say, okay, here's the area vector representing that plane. All right? The flux that is passing through this plane, if this is the angle between the area vector and the electric field, then the flux is, we usually write flux as capital Phi with a subscript E, is equal to E dot A. Okay? So remember from what we did previously with the dot product, this is EA, where EA, that's magnitude of the field, magnitude of the area, times the cosine of the angle between the two. Now this only works in this special case that I've given for a nice smooth plane. The area is a nice flat smooth plane. So if the electric field is passing this way, okay, you get some of it because you're taking that cosine of theta. If the electric field is in the direction of the area vector, meaning like, say you have a nice plane and the electric field everywhere is perpendicular to that plane, then the angle between the area vector and the electric field is 0. Cosine 0 is 1. It's just EA. Okay? It's just the electric field times the area, which has units of newtons per coulomb times meter squared, right? That's electric flux. If the electric field is in the plane, so in other words, if, say I have this nice flat area and I've got an electric field that is parallel to that area, okay, then the angle between the electric field and the area vector is 90, cosine 90 is 0, that's no flux. This idea of flux is how much field do you have passing through a given area. All right, you need a field, you need an area, and you also need that component of the electric field to be in the direction of the area, okay? You need some component of the field to be in the direction of the area. Just like remember when we had work, we defined it as F dot D, okay, or F dot R hat or some such thing like that. And you know that if that force vector was perpendicular to the displacement direction, that force vector did no work. And this is the same idea. If that electric field vector is perpendicular to the area vector, there's no flux. So this area vector is here. Well, let me use the field vector. All right, in this case where the angle between the electric field and the area is 90, no flux. That electric field is in the plane. But as I turn it, I get more flux, more flux, more flux, more flux, and then I get to the point where you have maximum flux. And that's where the angle between the area vector and the electric field is 0. Okay? So we're going to use this idea, we're going to extend this idea of flux, and I mean, we could do some calculations based on this, and I'll do some eventually. We're going to extend this idea of flux to things other than a nice flat plane, okay? Let's say you have, I'll go ahead and make it a sphere. Let's say there is a sphere, okay, like this. There's some spherical object and an electric field in the region. I don't know, maybe the electric field is this way, over here. It comes out here this way, okay, and it's everywhere. If I want to calculate the flux that is passing through this area, where the area would be the surface area of the sphere, I can't just look at E dot A because that area vector is changing. The angle between the area vector and the electric field may be changing throughout the sphere or on the surface of the sphere. Magnitudes may be changing. And think of it like this. Here's the little area vector maybe over here. Here's the area vector over here. Okay, something like that. All right. So this is changing throughout this region. To calculate the flux for an object like this, you have to integrate. Phi E is equal to the integral over the surface of E dot dA. Let me explain to you what this little bit of area means. I take a little section of the sphere, okay? So here's a little section, a little area for that section. Let me change that a little bit. That doesn't make sense. Okay, let me make it coming out like this. Okay, so maybe something like that. all right? So there's a little area vector. Then I look at this region that is here, okay? And that's my little bit of area dA, okay? So that little bit of area dA is something that is a small, I mean, you can think of it as delta A. It's a small little region, and at least locally, the area vector, this little area vector here, okay, is perpendicular to that little patch of area in that region, okay? So the area vector is changing as you move it all over the sphere or whatever surface you have, okay? So that's why you have to integrate. You're constantly taking E dot dA. You're looking at this dot product between the electric field and that little bit of area over the entire surface. Okay, and I'm about to do an example to show you how to do that. Okay. All right. So here's what I want to get to. Let us look at a point charge. So I want to calculate the entire flux of a point charge. Point charges have nice spherical symmetry. So remember, I'll use a positive charge like I usually do. Doesn't have to be positive, but okay. Here's a little bit of positive charge. And those are the field lines. So if I want to calculate the flux due to this, I'm adding up all that electric field around some certain area. I'm going to enclose it in an imaginary sphere. Okay? So there's my imaginary sphere. I know I'm drawing a little 2D slice, but I'm enclosing this charge in this little imaginary sphere. And these are the electric field lines. Okay. So I'm going to sum up the flux over this sphere. So what I have to do to find the flux is I have to do this, E dot dA. All right. So for this, I have phi E is equal to the integral over the surface of the sphere of E dot dA. Same thing I wrote over there. I'm just rewriting it here. All right, let's think about this. So at some particular radius from the center, here's a little r. There's some particular radius. There's some field strength at that point. Okay, we know how to calculate that for a point charge. That's kq over r squared. The little area vectors that I'm talking about, this would be dA. Okay? This would be dA. As you march around the surface of the sphere and you look at, okay, locally, I'm standing right here on the sphere, this big sphere that I live on that's Earth, and locally right here it looks very, very flat. And I'm going to represent that little bit of area with this area vector that's normal to the surface, and it's got a length, okay? It's a little bit, you know, it's got a dA. You can think of it as delta A, but it's a little infinitesimal bit of area. So here's dA over here. So I claim that the angle between E and dA over the entire surface of the sphere is equal to 0 everywhere. Because I'm adding up this E dot dA all over the surface. I'm summing up all the flux. Okay? So that angle is 0. So cosine 0 is 1. So this just becomes the integral over the surface of E dA. Got rid of the dot product, or took care of it. Okay. I also claim that at a given radius r, all right, at a given radius r, E is a constant. This point charge has spherical symmetry, and if I stay at this radius r, I'm moving around the surface of that sphere, this electric field magnitude is constant. So I'm going to pull that out of the integral. This is E times the integral over the surface of dA. Okay. What is the integral over the surface of a sphere? Well, that's just the surface area of the sphere. If I'm integrating little bits of area, summing them up over the surface, that's the surface area of a sphere. And you can find the surface area of a sphere, and you get, okay, phi of E. I'm continuing over here. I've got E times the integral of dA over the surface. Well, this is equal to 4 pi r squared. 4 pi r squared, that's the surface area of a sphere. So this is equal to E times 4 pi r squared. Okay? Well, we can leave it at that. But we're talking about a point charge. This is some point charge Q. We know the electric field at radius r due to a point charge. That electric field, E, is equal to KQ over r squared. That's the magnitude. I already took care of the vectors. Okay, it's equal to KQ over r squared. So I'll substitute that in. Phi sub E is equal to KQ over r squared times 4 pi r squared. Look what happens. The r squareds cancel, and this is equal to KQ, 4 pi KQ. Okay. But we can make another substitution because K is equal to 1 over 4 pi epsilon naught. So I'll substitute that in here. So phi sub E is equal to 4 pi times K, 1 over 4 pi epsilon naught times Q. 4 pi cancels. That cancels. It's equal to Q over epsilon naught. That is the flux due to a point charge. Meaning if I sum up all the flux, it's a constant, Q over epsilon naught. It's independent of how I sum it up. It's independent of the size of that sphere that I used. It's also independent of the shape of that sphere. Okay? I'll talk about that in a second. This is Gauss's law. Gauss's law is, this is the closed integral. So a closed surface, remember that I integrated over that closed sphere. So the closed surface integral of E dot dA is equal to Q over epsilon naught. This is Gauss's law. I hate 3 S's, but that's the way it's done. Sorry. Okay. This is a fundamental result of electrostatics. This works. It's a law. It works in all cases. It's independent of the shape of the surface. It's independent of the area of the surface. Okay? It says that if you sum up the flux over a closed surface, if you take E dot dA, this means closed, over a closed surface, you're guaranteed to get Q over epsilon naught. So I will write it as Q, that's enclosed. I'll put a little ENC in there. Q enclosed over epsilon naught. So for example, if you have, well, let me talk about this idea of the independence of the surface. Let's say that there's a sphere, and inside this sphere there is a fountain. This fountain is producing water. Now, where that water comes from, I don't know. It's got an endless supply, and it's producing it at a constant rate. So this water, let's say this is a membrane. This water is falling, and it's flowing out of the surface over here. And I calculate, well, how much water is flowing out of the surface over here? Well, that's the same amount that's being produced here. Okay? Let's say that the fountain changes. It's producing at the same rate, I'm in the same sphere, but the fountain changes its direction, and now it's got water flowing out here, 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 and over here. But I know that this fountain is producing the same amount of water all the time, and I calculate it on this surface. I know I'm going to get the same answer I had over here. Also, if I sum it up over some weird shaped surface, like this, same answer. If I sum it up over, I don't know, any surface you want to think about, closed surface, and I march around and I measure all the water coming out, I'm going to get the same answer every time. That's the idea of Gauss's law, okay? You have a nice closed surface. You're guaranteed that if you sum up the flux over that closed surface, you're going to get however much charge is enclosed in that surface over epsilon naught. Okay? So, if I take a surface like this, okay, and I have 2-point charges, plus Q and plus 3Q. Okay, so here's I'm going to make them little point charges. They're both positive. One is Q and one has 3 times whatever this one has. Okay, well we know that the electric field looks like this. It's nice and uniform everywhere over here, coming out of the surface, coming out of the charge. It's got that nice spherical symmetry. I know over here that this is a much 3 times larger, so it's a lot denser. So it's got, I'll draw some more lines, it's got a real intense electric field coming out. All right, I don't know. You get the idea, okay? Now, to actually do this integral is going to be a little bit difficult because this says march around this surface, and this I'm drawing a 2D picture, but this is a kidney bean or something that they're enclosed in. March around this surface and sum up E dot dA. Well, you've got angles that are all over the place, different, and here's the area vector here, here's E. That's going to be a task to sum up E dot dA. However, I'm guaranteed by Gauss's law that the total flux, if I sum it up over this entire surface, okay, then phi, well, I'll write it like this. In this particular case, over this closed surface, I really don't have to write surface because I know if I write dA, that means a surface integral. That's going to be equal to 4Q over epsilon naught. That's how much charge I've got enclosed. Now, actually doing the integral would be a chore. But I don't have to do the integral because I know it's a closed surface. Gauss's law guarantees me that if I do this integral, I'm going to get 4Q over epsilon naught. Okay? Now, if this were a negative bit of charge, I'm not going to draw the field lines, okay? Let's say that you have a positive Q and a negative Q. Same magnitude of charge, but opposite sign. We know from what we did previously that you get an electric field that looks something like this. Okay. All right. This goes out this way. I'm not going to try to draw all of this. Okay. So if I draw any surface enclosing, it's called a Gaussian surface. If I draw any surface, now these field lines, I've kind of drawn it. These field lines, something like this, okay. If I draw any surface and I calculate the flux, all right, this way, in this case, the closed surface integral of E dot dA is equal to Q enclosed. Well, I've got a plus and a minus. That is 0 over epsilon naught, which is just equal to 0. That doesn't say that there's no flux. There's flux all over the place. However, for that closed surface, the amount of flux that is leaving the surface is equal to the amount of flux that is entering the surface. For these area vectors that we've been talking about, the little dAs, they always point from in to out. So we have an inside, it's a closed surface, we have an inside and an outside. So the area vector is always pointing from in to out. Okay. Let's see how we can use Gauss's law to solve one of the problems, or a couple of the problems that we did previously. So we had the problem of a line of charge. Here's lambda, here's a line of charge, I'll make it positive, and it has some charge per unit length lambda, and I want to know what's the field at a distance. I don't remember the variable I used, but let's say you're a distance A above the wire. So this is a very, very long, okay, I'm not doing the finite wire, I'm doing the very, very long charged wire. So I'm up here at a distance A, and I want to know what is the electric field at this point. This setup has nice cylindrical symmetry. If I look at the wire, say from this end, or I slice it along this way, I know that the electric field looks like a point charge. Okay. I'm drawing it. I'm only going to draw 4, but the point I'm trying to make is everywhere along this wire, there are no components of the electric field that are along the wire. They all are radially outward this way from the wire. Okay? So here's what I'm going to do. I'm going to enclose this in a cylinder. Oops, I missed the dot, but doesn't really matter. Okay, here's a little cylinder. So I'm enclosing this in a cylinder. And I'm going to use Gauss's law to see if I can figure out what the electric field is up here at this point. All right. So I have to pay attention to the ends. This is the area of that end. This is the area of this end. Okay, remember back the first thing I talked about, if you have nice flat planes, then the flux through those planes, so these are little discs on the end, then the flux through those planes is just EA. Okay? It's just the electric field times that area vector. It's E dot A. All right. Then there's the area of this cylinder. So I've got this paper towel tube that is enclosing the wire. So there's some electric field. I don't know what it is. And there's a little bit of dA. Due to the nice cylindrical symmetry, I claim that all along the cylinder, the angle between E and dA is equal to 0. It's like I did with the point charge, where you had that spherical symmetry and the electric field vector and the little dA were in the same direction. It's the same case here. So when I do this integral, I've got the closed integral over that cylinder. I'll write down cylinder here. So over that closed cylinder of E dot dA, okay, well, that's going to equal the integral over the ends of E dot dA. I can't forget the ends. It says it's a closed area, plus the integral over that cylindrical part. And that, I took care of the vector, that's E dA, or I took care of the dot product, that's E dA over the cylinder. I guess, I don't know, my notation's not that great, but let's get rid of cylinder here. We're taking the integral over the entire closed surface. So I've got the integral over the ends and then the integral over the cylindrical part. I took care of that dot product and integrating over the cylinder itself. Now, let's talk about the ends. There is no electric field vector or component of the field vector that is along that area vector on the ends. So this, I hope you believe me, for each end, because of what we talked about as far as how the field is constructed for this long, thin wire, this is equal to 0. So this just becomes equal to the integral over the cylinder of EdA. Okay? I claim at this distance A, the electric field is a constant. I'm not getting farther away from the charge distribution or closer. I'm at a constant distance, and because of this cylindrical symmetry, that is a constant all along that cylinder. So I'll pull that out of the integral. So I get E times the integral over the cylinder of dA. All right. Well, what's this says sum up the area of that cylinder, the cylindrical part. So what's the area of this cylindrical part? Well, let me give it a length. I'll call that L. Okay. You're going to find that it'll be independent of the length, but for this calculation, I'll do the length. Well, that's just like stacking up a bunch of little circumferences, okay? So it's 2 pi RL, so this is equal to E times 2 pi RL. Okay, that's the distance around, and you add them up, L high. Okay. Back to Gauss's law. I did the integral. The integral was not difficult because I had that nice cylindrical symmetry. So I get E times 2 pi RL is equal to Q enclosed. How much Q is enclosed in this cylinder? Well, I know that it has some charge per unit length. So Q enclosed is equal to lambda L, right? That's the charge per unit length times the length. So it's lambda L over epsilon naught. Well, look at this. The L cancels. And I get, let me rewrite it down here. I'm calculating E, so I get E is equal to lambda over. I used R here. I meant to use A because that's the radius of the cylinder. Let me correct that. That's an A, and that is an A. Since I made the radius of the cylinder A, I need to use A here. So this is lambda over 2 pi A epsilon naught. Okay? And I think that's the same result that we got when we did that long integral for the wire, and then I let L go to infinity, and it took a long, long time. I think if you have a little bit of a grasp of Gauss's law, this was a little bit easier. This is the same result. Let me rewrite it. Remember that K is equal to 1 over 4 pi epsilon naught. Okay. So this is equal to 2E is equal to 2K lambda over A, because K is equal to 1 over 4 pi epsilon naught. So you get a 2K lambda over A. And that was the same result that we got previously. Okay? All right. Here's a real simple one, example that may not be quite as obvious. Here's that big plane of charge, okay? It has charge per unit area sigma, and I'll make it positive, doesn't have to be, I'll make it positive. And there's some electric field everywhere due to this charge distribution, uniform charge distribution. So there's an electric field, emanating from this plane everywhere. It's nice and uniform. So I'm going to show you how to quickly use Gauss's law to calculate that electric field. I'm going to turn this thing on edge. So if I look at it on edge, I'll redraw. Here's an edge view of the plane, and there's electric field here, everywhere. So what I'm going to do is I'm going to plunge a cylinder in this plane, an imaginary cylinder, a closed cylinder. So in this plane, I'm going to put a cylinder. Let me do it this way. Okay. My drawing skills are nil. Okay. So here's a little cylinder that is down through the plane. And of course there's all right, that's plunging through the plane. So if I draw that cylinder over here, it's going to look something like this. Okay? This is a large sheet of charge. I know from the charge distribution that the electric field is nice and constant throughout this sheet. Now, summing up, for Gauss's law, there's a little bit of area here. There's an area on the ends, and then there's some little dA here. So let's think through this. This cylindrical part in this case, unlike what we had with the wire, this cylindrical part, the area vector is always, that little dA is always at a right angle to the electric field. Another way to say it is the electric field is in the plane or in the same direction as the cylinder. Okay? There's no flux through that cylindrical part. There's no electric field that's cutting through the cylindrical part. So I don't have to worry about that. But the ends are a different story. For each end, since this is E, okay, for each end, you get E dot A and E dot A here. And the angle between E and A is 0, right? E and A, E and A. The angle there is 0. So you get all the flux through the ends. And this says add up all the flux. So you get E If I add up the flux in this cylinder, I don't have to worry about the cylindrical part. I get EA, that's the left end, plus EA, that's the right side, and that is equal to Q enclosed over epsilon naught. Just summing up the flux. This is 2EA, and that equals Q enclosed over epsilon naught. How much Q is enclosed? This has an area A. So that little patch of area has charge sigma A. Because sigma is the charge per unit area. Have a little bit of area A. So Q enclosed is equal to sigma A. So let me rewrite it up here. So I get 2EA is equal to sigma A over epsilon naught. The area cancels and you get E is equal to sigma over 2 epsilon naught. That is exactly the same result that we got when I did the disk the other day. So we calculated the electric field due to the disk of radius big R, and then I let R go to infinity, and in the limit we got this. This was a much faster, easier way to calculate that electric field with this idea of Gauss's law. Gauss's law says if you want to calculate the flux, you enclose the charge in a closed surface, all right? And then you integrate over that closed surface and you're guaranteed to get, so you're adding up all the flux, you're guaranteed to get Q enclosed over epsilon naught. Gauss's law always works. It's nice for calculations if you have some kind of symmetry, like spherical symmetry, cylindrical symmetry, planar symmetry, okay? It works. All right. So there's some problems at the end of that chapter on Gauss's law. If you need help with those, I'm glad to help you. We will return to some ideas from Gauss's law eventually. All right, that's it.